Welcome to Gradient Canvas. Today we're going to learn about how a single neuron is really just a movable decision line. Here are two kinds of points, reds and blues. Your whole job is to draw one straight line that separates them, just one line. It turns out a single neuron, the basic building block of every neural network, does exactly this, and it finds that line on its own. So let's take a neuron apart and see the geometry hiding inside it. Strip away the biology, and a neuron does something almost boringly simple. It takes your inputs, here, two numbers, x1 and x2. It multiplies each by a weight, w1 and w2, adds them up, and adds one more number called the bias, b. That single value, w1 times x1 plus w2 times x2 plus b, is the whole computation. We'll call it z. Now here's the move that turns algebra into geometry. Ask, for which inputs does z come out to exactly 0? w1x1 plus w2x2 plus b equals 0. If you remember your algebra, that's the equation of a straight line, so the neuron slices the whole input space in two with a line. And a line has two sides. On one side, z is positive. The neuron leans toward yes, class 1. On the other, z is negative. No, class 0. Right on the line, z is 0, dead, undecided. And here's the elegant part. The weights themselves, taken as an arrow w, always point straight across the line into the positive side. The weight vector is the boundary's compass needle. So what do the weights actually control? Their direction sets the tilt of the line. Watch as I rotate the weight arrow, the line pivots right along with it, always staying perpendicular. The weights choose which way the boundary faces. The bias does something different. Keep the weights fixed and change b, the line slides, keeping its exact tilt, sweeping across the space like a sliding door. The bias sets the position of the boundary, how high the bar is before the neuron says yes. Weights tilt it, the bias moves it. But a neuron doesn't just answer yes or no, it gives a confidence. That's the activation function. The weighted sum z is a flat ramp. Far on the positive side, it's big. Far on the negative side, it's very negative. The activation, here the sigmoid, squashes that ramp into a smooth S from 0 up to 1, and the decision line is exactly where the S crosses 1/2. Crank up the size of the weights, and the S sharpens toward a hard step, a crisper, more confident boundary. Shrink them and it melts into a gentle ramp. Let's make it concrete. Say the weights are 1 and 1 and the bias is -4. The boundary is x1 plus x2 equals 4. Take the point 3, 3. Z is 3 plus 3 minus 4. That's 2. Positive. So the neuron fires, and the sigmoid of 2 is about 0.88. Now the point 1, 1, z is -2, negative. The sigmoid gives about 0.12, class 0, and the point 2, 2 sits right on the line. Z is 0, sigmoid 1/2. The neuron is perfectly on the fence. But one neuron only ever draws one straight line, and some patterns simply can't be split by a single line. This one, where the matching corners share a class, is the famous XOR. Rotate the line, slide it, tilt it however you like. One corner is always on the wrong side. A single neuron just can't solve it. And that's the whole reason we stack neurons into layers. Combine a few lines and you can carve out regions no single line ever could. So that's a neuron, geometrically. A weighted sum plus an activation is nothing more than a movable decision line. The weights tilt it, the bias slides it, and the activation turns the crossing into a confidence. Stack these lines together and you start bending space itself, which is exactly where we're headed next. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts from neural networks to transformers. See you in the next video.